Hi, everyone. Thanks for joining our second day of Networking at Scale. I'm Neil Spring, part of the network analytics team at Meta. We work to instrument all the ways that our data center network is used and all the little problems that crop up. This is our live Q&A session with 4 speakers from the 2 talks we just saw. So welcome back, Abhishek and Balasubramanian, who spoke about managing data center congestion, and welcome back to Prashanth and Prankur, who spoke about a platform for customizing the transport protocol using eBPF. Behind the scenes, Yang Zhang, who will moderate the final panel of the day, is shepherding the questions that you submit my way. So please find that little feature within the Zoom client and submit. Just to start off, I am really excited about how well this worked out to focus on transport for this instance of networking at scale. We saw yesterday some great ideas of what you can do if you embrace the philosophy that you'll never get TCP to do what you want. So just like start over, build a new transport protocol, do it all user space, and forget about the kernel. And today, I think these 2 talks have shown what comes from a different philosophy enabled by BPF. Maybe you can override that little tiny bit of logic that you want, maybe edit the fields in the packets to make them right, maybe edit the transport state. If you're just allowed to modify what the kernel does, maybe that's a different way of getting the extensibility that you seek. And this turned out to be one of the questions that came in from our audience, is like contrasting these 2. Here, today's talks are where the focus is on transport header tuning in the kernel based on global policies or configurations. Do you see these 2 approaches conflicting with each other? This question was from Gagan Neha. Prashanth, do you want to start us off?
Sure. Thanks, Neil. So I believe these 2 are 2 systems at 2 different scopes. What we covered yesterday was more in terms of all the traffic that majority of the traffic that's going from clients to the entry point, the POPs and edge part of Meta. And here, whatever we covered now is more on stuff that's within the data center fleet of Meta. So here we have more control over both the endpoints, both the client and the server. So this gives us the ability to understand the stuff and possibly tune the right stuff within TCP itself.
Bala, do you want to add some perspective?
Yeah, sure. So I kind of feel there's a common theme and something that is unique in both. The common theme is we just don't want to live with what kernel can do. So that's why we are writing our own programs to override what kernel does, to make sure that we kind of tune what we want out of it, but still living with the kernel. While Quick does the same, but tries to get stuff outside the kernel and handle it by its own. That is what I feel is the common part between Quick and the transport. But again, there is still differences. Like for example, in environments like data center, where we want adoption to be much faster, relying on Quick or the technologies that is driven or required by Quick could take a while. So it is better to try these with adopted technologies like kernel rolled out everywhere or TCP-based changes, figure out that this worked, and then finally moving them to Quick would be a great way to progress in the transport.
Abhishek, do you want to take it too?
Sure. I think just to add to what has already been said, I think some of it is part of where the control lies as well. I think if we control the fact that we can easily upgrade the kernel to the latest functionality that is supported by it, that actually enables us to move in that direction. But if you have to get an agreement that everybody should have the same kernel, then it causes a little bit of friction where somebody may not be able to or may not have it right away. So in that sense, do you actually want them to suffer just because they're not able to update the kernel and so on? So there is a trade-off. I think in certain cases, we can actually, having the control, right, be able to roll things out with kernel upgrades. In other cases, it's better to build things on user land and make sure that everybody agrees to regardless of the underlying things. So both have that kind of an advantage, disadvantage as well.
Prankur?
No.
Okay. So let's go on to the next question. Abhishek, have you, when working on DC-TCP, have you noticed any interactions where DC-TCP makes those hardware offloads less efficient than they are with the loss-based cubic transport or cubic congestion control algorithm that those offloads were probably designed for?
Right. So yes, I think in some of the early experiments that were done, we did actually see that. So especially around the receive offloads aspect of it, when the packets are marked with the ECN bit, what we see is that the coalescing of these packets can only happen if all the packets have the ECN mark or they do not have it. So of course, with Cubic and other protocols that we were using earlier, the algorithm we were using earlier, that was not the case. But now with DC-TCP, we have to worry about this. Now, because of this, if there are intermittent packets that have the ECN bit set, then the coalescing will be that much smaller, and therefore the CPU has to execute on more of these smaller chunk of packets, thereby taking more CPU. So there are some aspects of it which do impact hardware offload.
And in this context as well, another question for you, Abhishek. There's this blind spot, and like I love the DC-TCP paper, but there's this lovely sentence in there. I forget exactly what it is, but it's sort of like, we're not going to deal with not data center traffic, right? You have a mix of data center internal traffic and data center external traffic, stuff that's either going to the outside world or just going to another data center. Mm-hmm. What happens when? What do you see happening when these two types of traffic interact?
Yeah, so this was actually one of the practical implications that we have to deal with in production networks, right? So we don't only have traffic that works within the data center, but we have cross data center, across regions, traffic being exchanged, and services, they want to do what they want to do, right? So we don't actually control that. So from a networking perspective, we have to accommodate this. And the switching devices have the shared queue where both traffic that is within the data center as well as coming across data centers is sharing the same queue. So what we ended up doing, as was seen in the presentation also, was a couple of different thresholds. So one for DC-TCP, which would use ECN-based thresholds, and then for Cubic, we will have tail drop. Now, there was some balance that we had to achieve in order to be able to achieve fairness in the network. We saw in our experimentation that the swing can be either way. So if both the thresholds are actually on the lower side of the buffer, what happens is that Cubic is not able to expand because RTTs are large and it cannot grow its congestion window. On the other side, if let's say the thresholds or the ECN threshold is high as Cubic, what happens is that we need a much larger burst to actually be able to signal the congestion in the first place. So there is a good amount of balance which we were able to achieve with experimentation, where we're having ECN threshold that is a little smaller to accommodate the intra-region traffic, and then for Cubic we had a larger threshold, but not as large as the buffer, in order to make sure that Cubic does not actually overtake the entirety of the buffer. So this balance was something that we had to deal with, and these were the interesting findings on how when we went to production, what are the roadblocks that came along with it.
Nice. So Bala, question from the audience. I think this is probably something that can be best answered by you. It was mentioned that some centralized control plane is needed for dynamic window tuning per service. Is this a sort of central controller-based approach? And what mechanisms can be used for service questioning? I'm not quite sure what that means, but hopefully you understand it.
Yeah, got it. I think I kind of mentioned that the part as one of the challenges that we had. Yeah. So yes, to answer this question, it was kind of a centralized approach as well as a distributed approach. We actually handled the centralized part just for the configuration management to make sure that we know and then we have one unique threshold for the entire service, rather than having one value for each of the hosts. While we relied on the distributed agent that was netted sitting on each of these hosts for us to feed what is a good threshold for each service on that specific host. So we kind of used the aggregated knowledge we collected from each of these hosts and had a centralized repo to control what is going to be deployed. We just went with the centralized approach to make sure that we don't want each of the hosts running a different tuning, a different value of tuning, to make sure that that would end up in a debugging nightmare. Let's say if for some reason the values keep on changing and we don't understand what is the behavior. So that's the reasoning behind going with that. I hope that should have answered this question.
So, and then I guess another question for you is how do you choose these values that you're setting kind of in a hyper-centralized fashion?
Got it.
Is there like a mathematical model? Is there a simulation? What do you guess and check?
Got it. I think definitely not guess and check. So yeah, we did have a mathematical formula that helped us to pretty much predict this for all the services that we were able to onboard. So that was actually directly proportional to the BDP or the speed, which in turn relied on the NIC speed. But it was also closely tied or inversely proportional to the number of flows. So this is where the complexity gets a little bit on to the second part of the question that you just had, is like, how do you know you are not clamping too much? Like, or how do you know that you are like not taking care of peak traffic patterns, right? So the part that we had to spend some more time on was to understand what is the P50 traffic profile as well as the P90, P95. And we tried to use them both. This made sure that taking in the P95 made sure to reduce retransmissions and help services to have better P99 latencies, while adding the P50 threshold to the formula helped us to make sure that we are not underutilizing the link.
Awesome. Kind of moving on toward the next talk. There's a question from the audience. I'm going to merge it a little bit with another question. It's like one thing that I've noticed personally is that eBPF is really great for small debugging tasks. Like if you can run a BPF trace program and get the information that you need, there are a lot of examples out there. It's really solid and great as a debugging tool. But NetEdit takes this like kind of debugging tool and uses it all the time, right? Using the information that it extracts and also changing things, not just debugging, but like actively modifying what's going on. And I wanted to ask about like what sort of challenges you run into. And one of our audience members asked, like, how do you roll out and roll back these changes? Is there a golden image? Do you manage it at the orchestration layer? I wonder if Prashanth, you can talk about these challenges.
Sure, Neil. So almost all of our work starts out with a simple eBPF program. But to deploy this, we have many factors to consider. I touched upon a few in the talk itself, like around hardware and service requirements. But the actual fun comes up when all the operational challenges we have once we deploy something. Like, how do you fail fast if you find a problem? Can you turn off a feature like in the order of minutes or less? And whatever feature you want is tied to a specific kernel version. How do you add conditions and checks into your enablement norms? Also, observability is a key area. Like, how do you get both the bird's eye view and also the ability to like drill down into specific connections, both at the same time? And the question that we're asking around packaging, overall, our method is around keeping things really simple, like building BPF programs, packaging them along with our binary that we ship. This way, we don't have to worry about different versions. The single binary version, when it's rolled out, has this BPF sort of like a golden image, and we can go and replace what is currently running with this particular version. And we kind of have knobs to like turn things off really quickly if the things go wrong, and that's where the policies come in.
Okay, Prankur, I've let you be quiet for almost this entire panel. So questions for you. First, like you described a little bit in one of your examples, what happens when you have two conflicting decisions that happen at the end of a policy. And I guess I'm curious if that's a real example, and what you think should happen if there are two like intentionally conflicting policies. How would your system deal with this?
Yeah, sure. So yes, definitely it was a real example. We had a feature depending on like ECN, which wanted the early congestion notification to be enabled for it to work properly. But another feature was inadvertently disabling the ECN, which resulted in like disabling our feature in like a few of the hosts. Because meaning like it was totally dependent on like when were those features actually started. So yeah. So if you think about it, like we have like control plane as well as data plane policies are active for a feature at a time, and we can have like conflicting policies in both the cases. For control plane conflicts, we solve it via the policy ID number. If we have lower the policy ID number, it would be into effect. And for data plane, we have like a chainer. So if you are attached into the chainer first, your changes will take into effect. And if you are attached after in the chainer, and if somebody before you already changed an existing thing, even if you change it, it won't be taken into effect. We have like a pretty much handling of like the double writer or triple writer scenarios in our chainers.
Brilliant. That takes out the follow-up question from the audience about needing to use a chainer. Awesome. So then the kind of second question for you is how have you instrumented the cost in like CPU or memory or overhead and broadly defined in applying these network tunings? Is it like comparable to just writing it in the kernel, or is it expensive enough that you only want to deploy it in a few places? How's the performance?
So from eBPF point of view, meaning like every attach point comes with its pros and cons and its associated cost, right? The example which I gave in the presentation was between like we wanted to like enable a feature. We first went ahead with the SOCOPS eBPF attach point, and we identified, okay, meaning the callback which we are using for that solution is resulting in a lot of callbacks for a BPF program, thus a lot of CPU usage. And then we like worked with like another attach point SOCOP, and we were able to like reduce the BPF CPU cost by a huge margin. So similarly, meaning like we have other attach points like TC attach points, right, which works per packet. Yeah, you will get a lot of freedom if you're doing it on a per packet basis, but it would be running on your per packet. Your BPF program would be running on per packet, thus using a lot more CPU as compared to other attach points. But meaning like, so we have like two features which were like AC based. So as they were like working per packet based, but for a connection, if we wanted to like store some information for a particular connection and avoid those all duplicate operations, we did it using an SK local map, but in order to save those CPU cost, but it would result in a little bit of extra memory. But again, meaning like it saved us in like a few of the features, but as we identified, if this SK local map was like increasing, we were running into like cache misses because of the locality issues. So meaning like everything has its pros and cons. We just have to identify what works at scale for us. Yeah.
Awesome. So I want to kind of the last sort of question, maybe start with Prashanth on this one. It feels like we're using BPF to avoid modifying the kernel directly, right? Like we can make changes and it can apply to even old kernels without waiting for any feature to go through testing and deployment, bundled together with all of the other changes that happen to be in a new kernel version. Is NetEdit like the future? Is NetEdit going to be there for 5-10 years? Are the features that are implemented in BPF going to stay implemented in BPF? Or is there kind of an idea that they would be like prototypes that would eventually migrate into ordinary kernel logic and just exist in kernel, 6.12 or something? And at which point we can pull it out. What do you think about the future?
So overall, right, the best software is the one that you've not written. In that sense, I think in the longer term, this keeps coming up in most of our long-term discussions. So I believe we have two kinds of things that we do. One is features that we implement in the kernel, which I think in the longer term makes more sense to be, once we know they are robust, we can move them into the kernel. Things like the condition controls that we implement could be something that we move it back to the kernel. And then there are all these knobs that we use to select and tune different things. These knobs, Linux has some really great ways to do this. Like, for example, you can add a route. You can pretty much change the condition control or anything else in the connection. But then services need something a little different. You need service-aware ability to know what to tune. So I think this still belongs closer to the application. And so maybe eBPF is the best place to do this. So I think it's a mix of both.
Yeah, that's awesome. I wanted to go around the room with this question, but I see now that we are kind of out of time. Thank you all, Prashanth, Bala, Abhishek, Prankur, for these great presentations and setting aside the time to share this morning. Thanks to our audience for the wonderful additional questions, and stay tuned for our final session of talks, which I will hand it off to Rajiv to introduce.